Now let's get started with this tutorial. This is the Tektron2 official repository and this is exactly the framework we are going to use today. I have used the Tektron2 many times in my projects as a computer vision engineer. I think it's an amazing framework, an amazing algorithm, and in this video I'm going to show you how to train an object detector using the Tektron2. Now the first thing I'm going to do is to show you the data we are going to use today. Now, we're going to use the same alpaca dataset we already used in one of my previous tutorials. If you watched my previous video on how to train an object detector using YOLO V8, then most likely you are already familiar with this dataset. This is exactly the data we are going to use in this tutorial too, and this is how the images look like. Now, it's very important that in my case, I already have the annotations of this data. You can see all of these TXT files. This is my annotations. These are my annotations for all my data, for all my images. But if you're watching this tutorial, then most likely you want to know how to train the Tektron2 on your own custom data. And most likely you want to know how to do all the annotation, right? You want to build this dataset from scratch. You want to annotate all of your images. And the annotation of an object detector dataset, it's something I have already covered in one of my previous videos. In my previous video where I show you how to train an object detector using YOLO V8. I think it doesn't really make a lot of sense to cover the entire process again in this tutorial, so if you are curious to know how to annotate your custom data, then go ahead and watch that other video. I'm going to post a link somewhere in this video. And now let's go to PyCharm, to a PyCharm project I created for this tutorial, and these are the requirements for this project. As always, please remember to install these requirements before starting with this tutorial, otherwise nothing is going to work. So please remember to install these packages, and now let me show you these three files. They are called train.py, util.py and loss.py. Let's start with train.py. This is the file we are going to execute in order to do all of our training process, and you can see it all starts with a very long docstring explaining how you need to format your data. This is very important. In the util.py and loss.py we have many different functions, and we also have a class definition. We have many different code. We have a lot of code which already handles the entire training process, already handles the parsing the data, already handles everything. So the only thing you need to do in order to make this training process to work as expected is to put the data into this format. To put your file system into this format too, you need to put everything as it's specified in this docstring. So let me show you. You can see that the annotations should be provided in YOLO format. This is this format, class XC, YC, which is the X and Y position of the center of the bounding box of the annotation, and then the width and the height of the bounding box. Now let me show you one of my annotation files. Let me show you how it looks like. You can see, for example, in this case we have 5 numbers. The first one is a 0, and then we have 4 float numbers. So this is exactly the annotation, the bounding box in YOLO format. The first number, the 0, is the class ID, which in my case is always going to be 0 because I only have one class in this dataset. And then these two numbers are the X and the Y positions of the center of the bounding box. These two numbers are the center of the bounding box, and then this number is the width, and this number is the height of our bounding box, right? So please remember to format all of your annotations into the YOLO format, which looks exactly like this. Class ID, X and Y position of the center of the bounding box, and then the width, and then the height. And then your file system needs to be structured exactly like this. Let me show you in my computer, in my file system. If I go to data, this is my root directory where my data is located. You can see I have two folders. One of them is called train, the other one is called val. Within train, I have two other folders. One of them is called images, and the other one is called ans. Within images is where I have all my images, all my training images, and within ans is where I have all my annotations for my training images. And then if I go to val, you can see exactly the same structure. I have two folders. One of them is images, the other one is ans. Within images, I have all my images, and within ans, I have all my annotations for the validation data. Now, this is exactly what's described here, right? You can see that we have a data directory, and within data directory, we have two folders, train and val. Within train, we have two additional folders, images and nonce, and the same about val, we have two directories, trains and nonce, and then this is exactly what I show you in my local computer. And then for absolutely every single image in this directory, we have an annotation files in this other directory with exactly the same name, but a different extension. This is very important, and please remember to structure your data, your file system exactly like this, otherwise nothing is going to work, because all the functions which are in this file, which handle all the parsing and reading the data and getting the annotations and so on, all of these functions are expecting the data exactly like this. So please remember to structure everything as it's described in this docstring, otherwise you are going to have issues in this training process. Now let's continue. If I scroll down, you can see I have this arg parser, and these are all the arguments we can specify, we can define for this training process. You can see that we have the data directory, obviously this is very, very important. Then we also need to define what are all the names of our classes. If I go to my file system, you can see that in my case I have this file which is class.names, and in my case it only contains one class name, which is alpaca. But if you are doing something like a multi-class object detector, then most likely you are going to have other classes as well. Now let's go back to PyCharm. You can see that another argument is the output directory. This is where all the models and all the results, everything is going to be saved. And then we have different hyperparameters. For example, the learning rate. This is going to be the learning rate of our training process. Then the batch size, the number of iterations of our training process. Then the device, if we want to do this training in a CPU or in a GPU, this is very, very important. Then this argument is the checkpoint period, which means how often we are going to save the weights of the model we are training, right? We are going to be training by this number of iterations, and a given number of iterations, every 500 iterations, we are going to be saving the weights of this model. And this is something we are going to see later on this tutorial when we are doing the validation of the model we trained. Now, another hyperparameter which is very, very super amazingly important is model. This is where we are going to specify the baseline we are going to use in order to do this training process. In my case, this is the baseline I have set. You can see it's Coco detection RetinaNet R101. And now let me show you something that's very, very important, which is where this model comes from. Let me show you in my browser. This is Detectron2 model SU and baselines. This is very, very, very important. When you are working with Detectron2, you have many models to choose from. So this model SU is basically the collection, a very, very large collection of all the baselines, of all the pre-trained models you can choose from when working with Detectron2. If I scroll down, you can see that we have many different sections. For example, here we have a section which is Coco object detection baselines. Then we have another one for instance segmentation. We have another one for key point detection. Then panoptic segmentation, and so on, right? We have many different sections for all the different type of algorithms, right? You can see that we have many models, many architectures, many baselines we can choose from. And basically the idea is that when we are training our own model, when we are training our custom model, we can just take whatever pre-trained model we want, we can take whatever baseline we want, and we can just train our own model on top, right? This is very important because you can see that we have many different metrics, or we have all the different performances of all of these different models. We also have the inference type, the inference time of all these different models. So this is amazing because we can just choose a model we like the most for the specific project we are working in. And in my case, this is the model I have selected. I have selected the RetinaNet R101. So this is the model we are going to be using in this tutorial. But in your case, please go ahead and choose whatever model you want, because it's basically the same. I mean, the entire process I'm going to show you in this tutorial is going to work exactly the same for whatever other model you want to choose from here. So this is the model zoo, this is the Tectron2, the model zoo, and please take a look at this zoo, take a look at all the models which are available, and this is just amazing. You can see that this is like a very large collection, and it's just amazing. So let's go back to PyCharm, and you can see that this is where you are going to specify the architecture, the model you are going to use in your training process. Now let's continue. You can see that after I just parsed through all of these different arguments, the only thing I'm doing is calling util.train. I am calling the train function, which is defined in my util.py file. And I am just calling this function from a very high level, right? I'm just calling this function, I'm putting all these arguments as input, and that's it. And this function is going to take care of the entire training process. If you have watched my previous tutorials on YOLO V8, the image classifier, the object detector, the instance segmentation model, the key point detector, absolutely all of my models, you will remember that the training process is super simple, super straightforward. The only thing we need to do with YOLO V8 is to code a couple of lines, and that's it. So for this video, for the Tectron2, I wanted to give you something that's like the same level of complexity, the same level of abstraction, right? I wanted to give you something super high level, which you can just go ahead and use without really caring about all the different details and about everything that's working under the hood, right? So that's why I made this train.py file like this, right? You can just set up all of your arguments, and then you can just call train. And you can just forget about all the complexity about using the Tectron2. That's something I wanted to do for you, because that's going to make things much simpler for you to just train your model on your custom data, and that's it. And I don't know about you, but in my case, the Tectron2, YOLO V8, or whatever other machine learning framework, algorithms, whatever you can think of, for me, they are only tools I use to solve my problems. Right? So being able to train an object detector using the Tectron2 by just calling a function like this from a very high level, for me is amazing. I don't know about you, but if you're anything like me, then you're just going to be super happy with this function. And if that's the case, then just jump to the next chapter, where I'm going to show you how to continue this training process and how to do this training from a Google Colab. But if you do care about the details, if you do care about how everything works, like under the hood, if you want to know exactly how these functions work and exactly how the data is parsed and everything, if you want to know more details, then just continue watching and I'm going to give you more details. And now let's move to util.py. You can see that we have 4 different functions, and these functions are the functions that take care of the entire training process. So let me start with train. This is the function we are calling over here in order to start with the training process. So this is a very good place to start with this util.py file. You can see that we have many different parameters, many different arguments into this function, and for each one of these parameters, for each one of these arguments, we have a very short description of what they mean, of what this parameter is. So this is very important, and please remember to take a look at this documentation, at this docstring when you are reviewing this file, when you are reviewing this function, because this is going to help you a lot to further understand what each one of these parameters and arguments mean. Now let's continue. We can see that the first line, we are calling another function. We're calling another function in this util.py file, which is register datasets. By the way the Tectron2 works, we always need to register the datasets before starting with the training process. Now let me show you this function, and this is another function in the util.py file. You can see that we are taking 2 parameters as input, which is the root directory and the class list file, and basically the only thing we're doing in this function is calling this method. We're calling dataset catalog.register, and we are just doing something else, right? We are just taking these 2 arguments as input into this function. But basically just remember that in this function we are registering the data, all of our annotations into the Tectron2. And this is a very important step when we are working with the Tectron2. You can see that we are registering the training set under the keyword train, and we are registering the validation set under the keyword val. This is very important because we are going to make a reference to these 2 words to train and val later on, so please remember. And then the second argument is this lambda function we have over here, and you can see that basically we are calling another function in this util.py file, which is called getDicts. So this is basically the function we are calling over here, and we are putting these two arguments, which is basically the location of the images and the location of the annotations for the training set and for the validation set. We are iterating in the training set and in the validation set, and for each one of these iterations we are registering each one of these sets. Right, now let me show you this other function, getDicts. And you can see that basically the documentation we have in this function is very proper. It's a very good documentation, and it says read the annotations for the dataset in YOLO format and create a list of dictionaries containing information for each image. The arguments are a directory containing images and another directory containing annotations, and the return is a list of dictionaries with all this information. The file name for every single image, and a unique identifier for every image, then the height and the width of the image, and then the annotations, the bounding box, and also the category ID, the class ID, right? And if I show you the code, it's very straightforward. The only thing we're doing is iterating in absolutely all the files in the annotations directory, and for each one of these files we are opening the image for this annotation, the image that belongs to this annotation, and then we are just taking the height and the width for this image, and we are just creating this dictionary with all the information, which is the image file name, the ID, the height and the width of this image, and we are just saving everything into a dictionary. And then the only thing we're doing is we are parsing through all the annotations, and we are just getting all the bounding boxes, and we are just getting also the class ID, right? So basically we are parsing through all of our data, and we are getting all the information of our images and all the information of our annotations. And something that's very important is that if you remember, our annotations are specified in the YOLO format, which means it's the class ID, and then it's the X and Y position of the center of the bounding box, and then it's the width, and then it's the height. And we are converting the annotation into another format, which is the XYWH in absolute coordinates. This is very important because this may be confusing, but just remember that we are taking the annotation which is in the YOLO format and we are converting into this other format. XY means that it's the upper left corner, and then it's the width, and then it's the height of the bounding box, right? So that's basically what we are doing here. We are converting the annotation from this format into another format, and then it's just getting the class ID, and that's basically all. And at the end of this function we are returning this list, right? This is a list of dictionaries with all this information, right? So just go through this function, and it's going to be super straightforward, and you have this super comprehensive docstring telling you exactly how everything works and all the input parameters and all the output and so on. So this is all for this function, for the getDicts. And now let's continue by reading register datasets. So after we register the dataset, the training dataset and also the validation dataset, then we need to tell Detectron2 exactly what are the class names, right? Because so far we are parsing through the data, we are parsing through the annotations, but we are only parsing through the class IDs, right? The annotations, they only contain the class ID, but they don't really have the class name. So it's very important for Detectron2, it's very important we tell Detectron2 what are the class names, and that's why we are calling this function after we register the datasets. So that's pretty much all for this function for register datasets, and now let's continue. So after we register the datasets, we can continue with the next line, which is getConfig. This is where we are going to create the entire configuration file we are going to use in this training process. And the first line is getConfig, and this is basically a Detectron2 built-in function, and basically we are getting something like a default configuration file with many default hyperparameters. That's basically what we are getting here, a very long, very comprehensive default configuration file. And then the next line, we are updating this file with many other values which are specific to the specific model we are using here, right? In my case, it's RetinaNet R101, and basically after we are getting this default configuration file, we are just updating this file with many other values which are specific of this model, right? That's very important. And then the only thing we're doing is just setting other values. We are just manually updating other values in this config file, right? You can see that for each one of the other lines, it's config dot a given key, and it's the value for that key, right? In this case, we are updating the value of the training set, the validation set, the test set, and so on, right? It's very self-explanatory, each one of these configuration values, right? For example, here we are telling the Tectron2 to use CPU. Here we are setting the weights of this model, which is basically the pre-trained weights of this model we have over here. And then we are just setting the batch size, the checkpoint period, which is how often we're going to be saving the checkpoints, the learning rate, and so on. And I would say this is the most important part of this function by far, right? Because this is where we are telling the Tectron2 where is the training data and where is the validation data, right? Because we have registered the data sets, and if you remember, we called one of the data sets train, and we called the other dataset val. So this is where we are telling the Tectron that the training data is the dataset we register under this keyword, train, and the validation data is the data, the dataset we register under this keyword, val. This is very, very, very important, and this, I would say, it's the most important part of this function. And that's basically all for this get config. Now let's continue. And you can see that then the only thing we're doing is we are creating the output directory. Then we are creating this object, which is the trainer with the one that's going to take care of the training process. Then this line, and actually these 3 lines we have over here, this is also very important because when we are training a model using the Tectron2, during the training process, we will have a lot of information regarding the loss function in the training set. But we will not have any information regarding the loss function in the validation set. That's the way the Tectron2 works by default. So if we want to add this information, if we want to add the loss function in the validation set, if we want to access this information, this is exactly what we need to do. And this is why I created this class we have over here, which is validation loss. This is the class which is defined in loss.py. So long story short, these 3 lines we have over here, it's related to creating this custom output, creating this custom debugging information regarding the training process, so we have more information regarding how the training process is doing, how the training process is going. And this is very important because this way we are going to have additional information, and this is going to be super useful once we are validating this model. So now let's continue. You can see that this line is resume or load, and this is pretty much if we are resuming this training or if we are training from scratch. And in my case, I'm training from scratch, so the resume equal false, and then the only thing I'm doing is calling trainer.train, and this is pretty much all it takes in order to start this training process, and that's pretty much all. So this is a much more detailed explanation of these 4 functions we have here in the util.py file, and also of the function, or actually the class definition we have here in loss.py. So this is all in order to give you more details regarding all these other functions and this class definition and so on. And now let's continue and let's go back to train.py, because now that we already have all the code we need in order to do this training, the only thing we need to do is to press play. And that's it. You can see I press play, I get some huge output. And this is, I'm just going to stop the training, I'm going to show you something. This is pretty much all the model, all the network, all the hyperparameters for this network we are using in order to train this model. In my case, remember, it's RetinaNet R101. And then the only thing we will need to do from now on is just wait until the training is completed. But in my case, I'm not going to train it locally because it's going to take a lot of time. I'm going to show you how to do this training from a Google Colab, because this is going to make the process much simpler and much faster. This is going to take care of the entire training process much faster if I will do it in my local computer. So I'm going to tell you how to do it from a Google Colab. The first thing you need to do is to obviously upload your data. And this is very important. Please remember to upload your data, otherwise obviously you will not be able to train this model from a Google Colab. And in my case, you can see that this is my data, the same data I show you in my local computer. These are my train and my val directories. And now you also need to upload these files, which are util.py, train.py, loss.py, and class names, right? So basically is these files over here, train.py, util.py, loss.py, and also the class names, which is this one. So remember to upload all these files, otherwise nothing is going to work. And now let's move to this Google Colab, to this Jupyter Notebook, and I'm going to tell you exactly how you can train this model from here. Basically, this is a very straightforward process. The only thing you need to do is to execute each one of these cells. So it's something very simple to do, and we are just going to be executing the code we have over here. The first step is to connect your Google Colab with Google Drive. So basically you need to execute this cell and you need to wait a couple of minutes. Click on Connect to Google Drive. I select my account. I scroll all the way down and I click Allow. And that's pretty much all. Then I need to wait a few seconds, and that's going to take care of connecting my Google Colab with Google Drive. Okay, so everything is completed. Then I'm going to continue with the next cell. I'm going to run this, install these requirements, which is running all this pip install. This is going to be very straightforward. The only thing you need to do is wait until everything is completed. Okay, that took a few minutes, but now it's completed, and you can see I have an output over here. You must restart the runtime in order to use newly installed versions, and if I scroll up, I got a similar output over here. So basically, remember to restart the runtime if you have a similar message, and that's going to be pretty much all. So the Google Drive is now mounted, so everything is okay. We have installed the requirements. Now let's continue. Then you need to change the working directory of this notebook. So you need to execute this cell, but it's very important you update this path to the path where you have uploaded the data and all of your files, right? In my case, is content, G Drive, my drive, and then this is the location of my data. If I show you my Google Drive, you can see this is my drive, Computer Vision Engineer, Train Detectron 2, Object Detector. And if I show you here, my drive, Computer Vision Engineer, Train Detectron 2, Object Detector. So please remember to update this path with the location of your data in your Google Drive. Your data and also your files, right? Everything should be located in the same directory. Once you have edited this location, the only thing you need to do is to press Ctrl Enter, and then that's going to be pretty much all in order to change the working directory. And then the only thing you need to do is to execute this cell. So you can see that we are executing the train.py file, and I'm setting these arguments, which are the device. I am setting device into GPU. It's very important because that's pretty much the reason why we are using a Google Colab, a Jupyter Notebook in Google Colab. So this is very important. Then I am also setting the learning rate in this value, and I am going to train for 6,000 iterations. I will say these two values, these two arguments are not absolutely needed. You can just use the default values, but in my case, for my data, for my problem, I noticed these values were better. It was much better to use this learning rate, and also it was better to do a shorter training. Only 6,000 epochs will be just fine. So now I have to press enter. I need to execute this cell, and that's going to be pretty much all to this training process. You can see how simple this is once everything is within this train.py file, right? Once I create these functions and I put everything in this util.py, we can just execute everything from a super high level calling train.py. And please let me know what you think in the comments below, but I think it's just amazing. We can just train Detectron 2 from a super high level as we are doing over here. The only thing we're doing is calling train.py, and we are passing the arguments exactly like this. From a super high level, we don't really care about the details, we don't really care about the complexity, we don't really care about nothing. It's amazing. I don't know what you think, but I think it's amazing. Please let me know in the comments below what you think. So this is pretty much all for this training. The only thing we will need to do now is we will need to wait until everything is completed, and this is going to take some time. This is going to depend on your data, on your annotations, on your problem, on your specific problem. In my case, for my data, it took something like 2 hours to do the entire training process. So we are not really going to wait until this is completed because I have already trained this model when I was preparing this tutorial. So let me just show you what the output looks like. Once you train your model, you are going to have a directory which is called output, exactly like the one I have over here. And this is where you're going to have all the results of your training process. You can see, you're going to see all of these models, all of these checkpoints, which are the weights of your process, of your training process in all these different steps, right? And this is where we are going to notice this argument over here, checkpoint period, because we have said that the checkpoints should be saved every 500 steps. And if you notice, these are all the checkpoints, these are all the weights we have saved, and if you check the numbers, you can see that these are 499, then 999, 1499, and so on. So all of these files are 500 steps apart. And yeah, so that's basically what it means to save the checkpoints every 500 epochs. At the end of your training process, or actually during your training process, you are going to be saving the checkpoints, the weights, exactly like this. So at the end of your process, you are going to have many weights files, exactly like I have over here. So these are my weights, but what I'm going to do is I'm going to take this file. This is the file with all the information of our training process in the training set and in the validation set. So this metrics.json file is the one we are going to inspect, is the one we are going to analyze to validate this model. So I'm just going to download this file. And now let's go to PyCharm because I want to show you this file, which is plotloss.py. So I have already downloaded this file and it's in my directory. Let me show you today's tutorial, Detectron2 code, and this is my metrics.json file I have just downloaded. And now if I show you this plotloss.py, basically what we are doing over here is parsing through this file, right? Parsing through all the information we have in this file. Let me open this file for you so you can see exactly how the information looks like. You can see it looks very crazy, right? We have a lot of values, we have a lot of information, and basically we need a way to parse through this information, and we need a way to visualize all this information super quickly. So that's why I created this plotloss.py, because it's going to help us a lot in order to just get all the information we want from this file and just plot everything into a very nice looking plot, so we can just do this validation much quicker. So let me show you how it looks like. I'm just going to press play. I'm going to tell you in a few minutes why I have commented these 2 lines. I'm going to press play, plotloss, play. And you can see that this is the training loss and the validation loss. The blue values are the training loss and the orange values are the validation loss. But obviously this is something that we cannot analyze because this is a lot of information. This doesn't really look very well, right? So we're going to do something now which is going to make everything much prettier, which is we're going to do a moving average on each one of these functions. Basically we are going to apply another function which is going to smooth these values, and it's going to make everything much smoother. I already made all the code we need, and I already made this function which is moving average, and the only thing we need to do is I'm going to delete these comments, and basically now we are going to plot the loss values, the same loss values we are getting from this metrics.json file, and then we are also plotting the moving averages, right? We are plotting the same functions but the averages. And you can see that this is how the averages look like, right? This is something that's much prettier. And in order to show you much better, I'm just going to remove these two plots, and we're only going to plot the moving averages, right? This is much prettier, this is much better. So now we have in blue the training loss. I'm going to adjust the labels. Okay, now you can see that everything looks better. We have these values over here. In blue we are plotting the training loss, and in orange we are plotting the validation loss. And we can see that both of these functions are going down, and that's a very good sign. But in the case of the training loss, it seems we have reached a plateau over here. So the training process, it goes super smoothly until it reached something like 5,000 steps. And in the case of the validation loss, it seems we also reach a plateau, but much sooner, right? So this is basically where we are going to validate this model, and this is also where we are going to decide which one of our checkpoints we are going to choose from this model, right? Because we have many weights, we have many checkpoints, and we can just use any of these files in order to produce our inferences, in order to produce our predictions. So this is where we are going to define exactly which one of these checkpoints we are going to use. And I would say I like how everything is going until this point over here, because you can see that the training loss is going down and the validation loss is kind of going down as well. And this is pretty much where everything is like a plateau, right? So if you ask me, I will keep this checkpoint over here in the 3000 epochs. So in the 3000 steps, this checkpoint over here. So this is where you're going to draw your conclusions and you're going to make decisions regarding what you're going to do next. Obviously, another conclusion could be to do the training again. It all depends on what's going on with your data. Ideally, your training loss and your validation loss should be like closer together, right? In this case, they are very far apart, and that's something I don't really like. But that's like ideally. I think that if we take this model over here in the 3000 steps, I think everything is going to be just fine. But ideally, I would like to have like these two plots more closer together, right? Because otherwise this could mean the model is overfit into the training data and the model is not going to perform well in unseen data. But never mind, let's just take this model, the one we trained over here in the 3000 steps, and let's see what happens. So I'm just going to get back to PyCharm, because now it's time to make our predictions. Now it's time to take the model we trained, to take the checkpoint we chose, and let's just make some predictions with this checkpoint, with this model. So let me show you how to do that. I'm going to this file, which is predict.py, and this is the file we're going to use in order to make our predictions. And you may see that everything is already coded, so everything is ready, and I'm just going to explain absolutely every single line of this file so you understand exactly how it works and you understand exactly every single line of this file. You can see that the first few lines are a few imports, so I'm just importing a few functions which are important in order to make these predictions. These are a few imports from Detectron2, and I'm also importing CV2. Then the first line is getting a configuration file. Absolutely every single time we use Detectron2, we need a configuration file. We need an object which is going to contain all the configuration for the specific task we are going to do with Detectron2. In this case, we are just getting this default configuration file with a lot of default values, and then we are updating this file, this default configuration, with many other values which are specific to the model we use. In my case, as I used this model, as I used this pre-trained model, this baseline, I have to use exactly the same one here, and the only thing I'm doing is updating this default configuration file with many other values which are specific to this model. Then, this is very important, I am setting the model.weights to the location, the path of the checkpoint we are going to use. And if I show you my Google Drive, remember these are all the checkpoints we generated with this training process, and as I am going to use the one we generated at the 3000 steps, this is the one I have already downloaded and it's already in my file system. You can see that this is the directory, the folder of my PyCharm project, and this is the file we are going to use. model/0002999.pth. So this is exactly the file we are going to use, and this is exactly the location of this file. Then, as I am going to make these predictions in my local CPU, I am setting device to CPU. Then I am creating this object, which is this predictor, and basically this is going to be the predictor we are going to use in order to make our predictions. Then I am loading an image, very important because we definitely need an image if we are going to make predictions, and this is the image I am loading. Let me show you. This is exactly the image of an alpaca we are going to use in order to make predictions. Ideally, we should be getting the location, the bounding box of this alpaca. Let's see what happens, but this is what we should get. Ideally, we should get the location of this alpaca. And this is the location, the path to this image, right? You can see it's data, val images, data, val images, and then it's just this name. If I search, you can see this is the image we are going to use. Now let's go back here, and then the only thing we need to do is to call predictor, and we need to input the image we are going to predict, and then we are just going to get all the outputs, right, all the results. But let's just stop for a minute and let me show you exactly how output looks like. I'm just going to print outputs. I'm going to comment everything else. This is maybe the only coding I'm doing in this tutorial. So I'm just going to press play. And you can see that this is the output we got, right? So these are the predictions for this image. You can see that we have many different fields. One of them is pred boxes, and these are basically all the bounding boxes, all the objects we are detecting. This is the first one, and then these are all the other objects. We are detecting something like eight different objects in this image. And this is very important. These are all the bounding boxes, and these are the X and Y coordinates of the top left corner, and these are the XY coordinates of the bottom right corner. So these are the bounding boxes. You can see that we are also detecting the scores. We are also getting information regarding the scores, the confidence values of each one of these bounding boxes. For example, the first one is 88.6% and the last one is 5%. So you can see that these are all the different confidence values. And then we are also getting this information, which is the class we are predicting, right? In my case, I'm only using one class, which is alpaca, and it's encoded with the number 0. But this is where you will have all the different numbers of all the different class IDs of all the objects you are detecting. And please mind that in my case, although my dataset contains only one class ID, because I'm only detecting alpacas, you may notice that some of these objects were detected with a different class ID. I have a 39, 47, 56. I have used Detectron2 many times in many projects, and this is an issue I have found in different projects. So you can see, for example, in this case, I should be getting only zeros because I only have one class in my dataset, but I'm also detecting other random numbers. So please take a look at the numbers you are getting here, and please take a look that everything makes sense, and just make sure you are only detecting the numbers you should be detecting. And if you are getting some random numbers, as I'm doing right now, just don't use those predictions. Do something like an if, something like that. And if the number you're getting is not within your predictions, it's not within your classes, then just don't use those predictions. Do something like that. But also in my case, for example, now you can see that the random numbers, the random values are some detections with a very low confidence. For example, this one is the fourth one, so 1, 2, 3, 4, this one, which is something like an 8% confidence, and then this one, which is a 5.8%, and this one, which is a 5.3%. So I guess it's most likely this is going to be an issue with those objects with a very low confidence value, but you never know. So please make sure the numbers you are getting, they make sense. Now let's continue. So I show you the output you are getting from Detectron 2. Now I'm just going to uncomment everything and I'm going to continue explaining this file. So you can see that the next line, it says threshold equals 0.5, and this is the detection threshold we are defining. So we are only going to consider valid all of those detections with a confidence value which is higher than 0.5. Now let's continue. You can see that this is basically we are parsing through the outputs. You can see that we are detecting 3 objects: the pred boxes, the scores, and the pred classes, right? So the only thing I'm doing is I'm parsing through this information and I'm just getting these objects: pred classes, scores, and bounding boxes. And then I am iterating in all the bounding boxes, and for each one of these boxes I am getting the score, the confidence score of that specific detection. I'm getting the class ID I'm detecting, the number of the class ID I'm detecting, and then if the confidence value is greater than the threshold, then I am just getting all the values, the XY position of the top left corner and the bottom right corner, and then I'm just drawing a rectangle on top of my image. I'm not really checking that I am getting only zeros. I am not doing it here, but that's a very good homework for you. I invite you to make an edit into this file, and you make something like an edit, for example here, and you say something like, if the confidence score is greater than the detection threshold and pred is within the class IDs of my class.names file of this file over here, right? If the prediction we are getting is within my classes, is a valid number, if I'm getting a number which makes sense, then and only then draw the bounding box, right? That's a homework for you. That's a very good homework for you. So yeah, I'm just going to continue, and you can see that I'm drawing the bounding box, and then the only thing I'm doing is plotting this image. So let's see what happens. Now I'm going to press play, and let's see if we are detecting this alpaca properly or not. Amazing! We are detecting the alpaca super properly. Remember, this is the image we are using, and we are just detecting the only alpaca we have in this image. And yeah, we are just drawing the bounding box, and the bounding box is enclosing the alpaca super properly. So everything is working just fine. So this is going to be all for this tutorial. This is exactly how you can train your object detector on your own custom data using Detectron 2, and this is going to be all for today. My name is Felipe, I'm a computer vision engineer, and these are exactly the type of projects and the type of videos I make in this channel. If you enjoyed this video, I invite you to click the like button, and I also invite you to subscribe to my channel. This is going to be all for today, and see you on my next video.